It's about time to start today's virtual dialogue talk. My name is Zhongyi Ho. I'm from the Chinese University of Hong Kong. I'm also the VP conferences and also the dialogue managers of IEEE CEDA. It's my great pleasure to introduce my colleague, Professor Bei Yu. We are in the same department. Okay, we know each other and we actually collaborate for many researches and the papers. Okay, so I know him very well. So let me uh, briefly introduce him. Okay, Professor Yu, he will be the professor. Okay, start in this August. Actually, very soon. Okay, after 2 weeks, he will be the full professor in our department of computer science and engineering, and he's also currently an assistant dean in the engineering faculty at the Chinese University of Hong Kong. His research interests include machine learning and deep learning with applications in electronic design automation and computer vision. He ever served as the TPC co-chair of ACM IEEE workshop on machine learning for CAT. Actually, I think everyone knows the ML CAT 2019 and also the International Symposium of EDA, ISEDA in 2025. He and And of course, he acts as the program committee and the track chair of DEC, ICCAD, DET, ASP.DEC, ISPD, and AAAI. And he is currently the associate editor of IEEE TCAD, ACM Totals, and the Integration Review Side Journal. Professor Yu, he's definitely I would say he is actually superstar, okay, in the EDA, especially on the machine learning EDA or LLM for EDA, okay, for this hot topic. So one more thing I would like to mention that he actually have more than 10 best paper awards in our major conferences. Okay, he's really, really good. So the time will be yours. Okay, Professor Yu, please go ahead.
Okay, thank you, Zhongyi, for the warm introduction. So today I'm really happy to be here presenting our long-term research about the AI in EDA. So basically the title will be a large language model in EDA. I will basically discuss the past and present the research about AI, EDA, and the future direction. So here is the outline. Past, I will discuss some machine learning application in EDA, and current state of the art, I will mention a large language model as a new methodology and its application. And in the future, where will be the new direction? And let's see. So before we discuss the machine learning, before we discuss how we apply machine learning into EDA, let's see the whole EDA flow. This will be a very long flow starting from system specification. Then later we will go through architecture design, RTL design, logic synthesis, and physical synthesis. In each stage, we will go through verification and testing. Later, we will go through the verification and packaging and testing. And in the early stage of the design, because we don't have very formal data, and the typical way we try machine learning is that we extract the manual feature, then we apply some classical machine learning methodology like ANN or support vector machine or the Bayesian optimization Gaussian process. So one particular example is in RISC-V architecture level design. Given the tree cell design, we actually can extract some important feature. When we tune the feature, we can synthesize and generate a new RISC-V architecture. And one classical example is the ISCAD 2021 paper, BOM Explore, and appreciate their contribution from UC Berkeley. And this paper try to explore the design space, applying some methodology. By this way, we can find a good Pareto curve to balance the power, clock, and timing, and so on. Because at this time, we don't have very formal data, and the feature is extracted by the designer. And later, when we go into the RTL or logic synthesis design, and then one classical methodology will be graph neural network, because we can model the netlist as a graph. In each node, in each stem cell, we can model that as a one node. And in the netlist, when two cells are connected, we will build out one direct edge in the graph. So the first example applying the graph neural network into EDA domain was like 5-6 years ago. Published. The work was published in DAC 2019 from the collaboration with NVIDIA. The work basically trying to identify some nodes in the netlist to be replaced by by a new cell. By this way, we can improve the testability or observability in the design. But when we change more gate, we will increase the power area. So we should have a trade-off, pick out the most suitable cells. And from the learning perspective, this will be a node regression problem in GCN. And another example happened in logic synthesis. This work was from the EPFL. And this work think about in the logic synthesis, we basically have the technology node independent optimization and technology node dependent optimization. In the early stage, we transfer the netlist into the internal data structure or representation. The typical one will be AIG. Another option could be the MIG or MXG or others. And this work is thinking about which will be the best representation. So at the very beginning, this work will try the partition the whole netlist into several components. And then for each components, we think about who will be the most suitable one. For example, one component could be represented by AIG, another one could be represented by MIG. By this way, different representation lead to different optimization result. And by this way, we can find a better way using this kind of heterogeneous representation. Another work will be a very famous work by Google. There are lots of discussion about this work, and people know this work applying the reinforcement learning to do microblock placement. But one additional feature is that before we fit the net circuit into the reinforcement learning policy, this work tries graph neural network to do classification. So basically, given the netlist along with the micro information and also some others, and this work will think about which policy may be most suitable for this work. For example, the CPU and GPU and DSP block may go to different policy. So after the netlist level GCN can work, we will go to the next stage, physical design. For physical design, one common sense is that now we can see layout, and layout could be viewed as an image. And people will be very happy because we can leverage the new idea of methodology in computer vision into this domain. Right. One very successful work was published in ICCAL 2018 from the Professor Zhi Xie. And he leveraged the segmentation framework into the so-called route net to do the routability prediction. So given the layout in physical design stage, we have the stencil, we have micro block, we have pins, and we also have some fluidity, which will be the manual features. And all this information will be separated into different channels. So based on this way, we can construct a 3D tensor structure, which will be very, very suitable to be handled by the convolutional neural network. And later, we will output the feature map to identify the region where could be the readability hotspot. There will be one future following work discuss what will be the new challenge or special challenge in EDA. One new thing is that different from computer vision part in the EDA, we are handling much larger layout. So this work, I believe it should be inspired by UNet. Basically, we will extract the feature from different granularity. And this work different from UNet, this work will only majorly do downsampling. Because the layer is super large, we will step by step doing the downsampling to extract the high level. Meanwhile, small the size of the image. And by this way, we do the segmentation, identify those readability hotspots. And this work will be, I really like this work because this work is the first work to discuss the major difference between the EDA learning stuff, the learning task, and their computer vision learning task. In computer vision, we mainly focus on the accuracy. We're trying to identify, we will do the object detection, we will do segmentation. By this way, we're trying to improve the accuracy. But in EDA domain, accuracy is important, but accuracy is not all the things we want. The major task should be optimization. So the prediction accuracy could be one thing to lead into good optimization, but accuracy itself may not be that important. For example, 95% accuracy or 96% accuracy, which one will be more important? It's hard to say. This work is thinking about after we predict the hotspot or something, we trying to extract the gradient using the chain rule. We will provide the gradient to the very early stage in this work. The early stage will be the sensor location. So so the main idea is that to think about a good readability, we provide gradient to all the stem cells. And if we leverage this thing into the global placement, we will think about this is the scenario. For each cells in the placement, for example, the cell here, if we try to optimize for violence, you will receive a gradient toward one direction. If we try to also optimize the congestion, we will receive another the gradient in another direction. And then when we consider the readability, the third direction, and when we also trying to optimize for timing, we will receive the fourth direction and so on and so forth. By this way, we can tune the importance of different gradient. By this way, we can combine all the considerations into the global placement stage. So this table summarizes the major difference between the classical or traditional EDA algorithm and machine learning. In classical EDA algorithm, after a few decades of development, we have better understanding for each problem. And so we basically try divide and conquer manner to divide the whole design stage into several very classical problems like placement, routing synthesis, clock tree synthesis. And we have very clear and smart abstract for this problem. This is a very good thing, but the bad thing is that we are looking at a very simplified problem. Because, for example, timing is the major things we're trying to optimize, but in the placement stage, we optimize the wireless. By this way, we hope the timing can be better, or we optimize for area. By this way, we hope that the timing could be better. In the logic synthesis stage, we're trying to optimize the level, the netlist depth. By this way, we can hope the timing could be optimized. But this is way too simplified. On the other hand, using machine learning, we can rely on the data to consider the more accurate timing information into early stage. But the big problem is that it relies too much on the data, not leveraging the mechanism of the problem. And here, when we summarize the previous story of the machine learning in EDA, I try to discuss a few challenges only happen in EDA domain. The one challenge is a circuit representation. This could be a very hot topic now. There are many ongoing work toward this direction. So let me give you one concrete example. Say why the circuit representation could be very different from the classical machine learning domain. We know that the graph neural network could be modeled the circuit, but let's see the situation. When we try to measure the similarity of the graph or similarity of the circuits, we look at this example. In the netlist A, we have 3 nodes and several connections. In other 2 netlists B and C, we have a slightly different structure. Let's think about which 2 netlists could be more suitable, more similar. And when we look at A and C, we think about, oh, maybe A and C could be more similar because there's only one inverter difference here, and all others are the same. So if we leverage a classical graph neural network here, when we leverage classical aggregation kind of operations, we will generate the graph embedding that A will be more similar to C. But if we really look at the gate here and think about the Boolean function, we will realize that from the truth table perspective, A and B are the same. And if we don't care about the timing information, if we should say the feature of the graph or netlist A and feature of netlist B should be as close as possible. So this will be a huge difference and make the circuit representation learning a special and challenging thing in the learning domain. So how we can leverage the Boolean information into the circuit representation? One very classical example is about for example, we can try De Morgan's law to do the circuit transformation. We transfer one circuit and change all the local part step by step. By this way, we can generate a sequence of the new circuit, and all of them are with the same Boolean meaning or Boolean function. By this way, we generate a bunch of the positive case or positive sample. So if we know the positive sample, we can do some additional random change. By this way, we generate the negative sample. If you are familiar with the contrastive learning, you will realize that as long as we can construct pairs of positive samples and negative samples, we basically have enough information to guide the training of the future. So when we are given 2 positive circuits, we were trying to extract 2 features, and meanwhile we hope the extract features should be as close as possible. On the other hand, if we are given 2 different circuits or negative circuits, when we get the 2 features, we hope the difference of these 2 circuit features should be as large as possible. By this way, we kind of inject the Boolean information into the feature we learned. And this could be a very important way to pre-train a model. So given a bunch of the circuits, we do this kind of the data transformation, get a bunch of the positive pairs, negative pairs, then we can pre-train a graph neural network. Okay, and later after fine-tuning, we can go into downstream task to do the node level classification or graph level classification. So this is the special thing. Another second challenge I want to highlight is the timing modeling. If you are familiar with the graph neural network, you will know that for graph neural network, it basically can only do 2 things. One is node level task. The second one will be graph level task. So, but when we look at the timing, by the way, timing is the most important thing we want to optimize. Okay, if the timing cannot be satisfied, the functionality could be wrong, right? So when we model timing, we have several levels. For example, within the stem cell, we should model the cell path. And about the net list level, we were trying to model the timing path along the cell and interconnection. Even given one net, we're trying to model the wire path. And for all of the timing modeling thing, we can construct a graph from different granularity. So can we directly apply GCN to model timing? The answer could be or may not be perfect. The reason is that, as I mentioned, GCN is only good for node level classification or graph level classification. But for timing, we should look at the path level, which will be very different from graph level. Let me discuss a little bit why GCN is only suitable for graph level task. Because when we try the training or inference in the GCN, we will go through a bunch of layers, and each layer we basically do aggregation and encoding. So this is a very concrete example. Given the graph on the left side, okay, when we do aggregation, so basically for each node, we try to get the information of its neighborhood directly, and we concate all the neighborhood information and its local information, combine them into a 1D vector, and then we do encoding to transfer the one-dimensional 1D vector into a higher dimensional 1D vector. By this way, for example, after one layer for node 1, you get the direct neighborhood information, node 2, node 3, and node 4. And after one more layer, node 1 will get the neighborhood with all the distance of 2 neighborhood information. Okay. And then we think about the aggregation and encoding. We basically extract all the neighborhood information. We have no idea about the passing. We cannot say, oh, this neighborhood is important regarding timing. This neighborhood is not important about timing. Typically, we don't do this way. How we model the path information? One interesting work was published in date 2023. And basically, this work will encode the path information directly. For example, here, it lists all the path information. For example, in the wire delay, there are 2 passes. So it will construct the path feature as a 2 the dimension, the 2D matrix, and the one dimension is 2. Okay, and along with the other GCN data structure like node feature matrix and adjacent matrix, and it will modify the forward and backward things. By this way, after training, we will get the path information. And this kind of thing, this kind of idea could only be applying to wire delay prediction, because in general, netlist, there are too many passes. For example, given a netlist with n nodes, the total path number could be exponential with regard to the n. So basically, how we accurately model the timing information given a netlist is still an open question. The second challenge I want to mention is about the netlist and layout. So because when we look at the layout information, we know that we can leverage vision model to extract the layout, to transfer layout as the image. But we also have the netlist. Why not we combine both of them together? So this is so-called GCN process, GCN. One concrete example, basically the first work was published in DAC 2023. This work extract both the netlist information and the layout information. And once we get the embedding from both sides, they will do concatenating them together into a unified feature, and then we do the following regression and prediction task. The fourth strategy or hot topic is called a constraint AIGC. AIGC basically is a hot topic, but in EDA domain, we also have our AIGC, which is a layout or pattern generation, but very different. It has a lot of applications like the manufacturability testing, or it could be a way to generate the benchmark to test the hotspot or OPC agent. But very different from classical AIGC in the EDA domain. When we generate pattern, we should make sure the pattern could satisfy the design rule. If you look at the design rule deck before, you will realize there are thousands of pages of design rules describing the special width, spacing, and the enclosure thing. And can we really leverage the learning model to precisely predict whether design rule is satisfied or not? Basically, the answer is no. There is still a huge gap between discrete design rule and continuous DM models. So to leverage, to solve this challenge, and in the pattern generation work, starting from 2019, we trying to separate the whole thing into two small tasks or two steps. The first step will be the topological generation. So we leverage the switch pattern representation, and basically we generate the topologic. And later we try the 2D legal pattern assessment to enumerate the width or different spacing of the topology to generate very diverse patterns. Okay. So after discussing the past about the machine learning plus EDA, let's discuss the large language model. This could be a very hot topic or buzzword now. So long time ago, when we communicate with computer using the command line, people call this a CLI, command line interface. Later we have GUI. This is called a graphical user interface. Now, when everyone is talking about the large language model, when we think about its interaction with the human being, someone called this CGI, conventional user interface. And I'm sure everyone has seen this picture before. This picture is from a survey about large language model. So basically, it lists many important and famous large language model along the years. So we can see there's a curve here indicating the year and months. So starting from 2019, we got the T5 from Google. In 2020, we have GPT-3. In 2021, we have the GPT-4, and later there are more and more, and many there are large language models. So this is a very heavy picture, but I would like to mention two information. The first information is that when we look at the yields, we will see that after 2022, there are more and more. There are many emerging large language models, but after 2024, there will be less pre-trained large language models, because many companies may realize that instead of the pre-trained large language model, they probably will go to special domain, think about how they can build out the fine-tuned model or do the agent stuff. This is one information. Another information is that for the different model, some names are highlighted in yellow color, which means this model is open source. And we can think about which model, which company is not is most close the company. So basically, probably you will realize that OpenAI is not open that much. Okay, so this is from the timeline perspective. From the structure perspective, this will be another important and famous picture, classifying the models into basically 3 categories. The red one is called the encoder-only large language model. The middle one in green color is called the encoder-decoder structure. On the right side, the blue one is the decoder-only structure. When we look at the encoder one, we see some very famous name like BERT. By this way, it only has encoder to given their content. They have encoder to extract their embedding feature. By this way, we have the better understanding. So we can treat encoder-only model as a kind of modeling model. Okay. And for encoder-decoder one, so basically we will have the encoder first, followed by a decoder. One concrete example is about the language translation. Given the language A, using encoder, we transfer into the embedding, and later using the decoder transfer. By this way, we get the target language. But in many large language model scenario, we only need decoder-only model. One way is that decoder-only model is easier for training. Another way is that, think about the scenario, when we say the question to GPT, like write an article, the question doesn't need too much comprehensive encoding, but the GPT will generate a very long answer. So decoder-only model has wide applications nowadays. And we also see many famous decoder-only model like this one. And then let me discuss some 3 classical large language model application in the EDA domain. The first one should be the Verilog generation or RTL generation, because in the large language model domain, we realize it could be very powerful for programming or code-gen or copilot. And when we look at the EDA part, we realize that RTL generation is more like programming generation. So this could be a very hot topic. Today, I cannot provide very comprehensive survey in this one because there are many works, and actually every week there are several papers published in archive. So it's really hard, if I cannot say impossible, to list all the recent work. But I only want to mention one work called Beta V. This is the first work published in top AI conference in this topic. This is following my philosophy. Instead of from academia, my philosophy is that instead of getting data or clean data, we should think about more from the methodology perspective. And this work kind of answer the question, how really we can get enough data to fine-tune a model. Enough data, we get data, not mean that we need more the human being to label data manually. Instead, they try to leverage the similarity between the Verilog code and C code. The idea is that this work grabbed quite some data or Verilog code from online or public data set. Because all the Verilog code has no labeling. How we label them? They use a tool called V2C to convert all the Verilog code into C programming language. And then we leverage the knowledge of the C code from the large language model using instruction pruning. So basically on the right side is an example. That's our system prompt we set to in the fine tuning. We said you are an experienced Verilog engineer. This is the input the Verilog code and trying to transfer the Verilog into the C code. And so basically on the left side is all the Verilog code we get from online, and the right side will be the V2C output. By this way, we can fine-tune the large language model to leverage the C knowledge into Verilog. Okay, and also by this way, we don't need very heavy human labor effort. Okay, the second example is called the flow script generation. Basically, this work was the first large language model work published in TCAT. Because my background is from back-end EDA, when we see the large language model, we were thinking about what sense can large language model really help the EDA? Can it help to solve the placement problem, routing problem? Unfortunately, nowadays it's really hard to do this. So we think about maybe we can fine tune a model to do EDA flow, the tuning or EDA flow generation. So basically, we train a model called the automage, and given the user requirement, it will generate the API. Basically, it will generate API to call the EDA tool. Okay, there are two basic questions to think about. One is how we get data. The second question will be how we make sure the model is robust whether it could be transferred from one EDA flow to another EDA flow. For example, if we have trained data in the cadence flow, whether we can transfer that smoothly into Synopsys flow, or transfer from the open source EDA flow into the commercial EDA flow. So to handle the transferability, this is what we do. We generate a bunch of the API by ourselves. Basically, we carefully think about all the possible API from the flow planning, placement, routing, and cross-tree synthesis and other stages. And by this way, we fine-tune the model, only generate our own API. And later we do lots of the software engineering to translate our own API into the third-party API. The third-party API could be from an open source flow or any commercial flow. The second problem will be how we get data. We basically generate data by calling the GPT 3.5 and GPT-4 when we have the careful prompt, we may generate thousands of the instance, and then we will do the cleaning to get the more accurate data. Later, all the data will be used to fine-tune Llama 2. By the way, when we did this work at the time, probably 2 or 3 years ago, at that time, Llama 2 was the most powerful open source model we can fine-tune. And during fine-tune, we try and kill LoRa, quantize the LoRa same. And when we verify the effectiveness of our fine-tune model, we don't compare it to Llama 2. Instead, we compare our fine-tune model with much more powerful closed source the model at the time, like GPT-4, Cloud 2, and GPT 3.5. So we do evaluation using 3 grades. Grade A means that planning and script are both correct. Grade B means at least the planning is correct. And for our fine-tuned model, we get 85% of the grade A result, much better than GPT-4 at the time. This is an indicator that at least the EDA flow fine-tuning could be a useful application. We fine-tune the model comparing to the pre-trained the model. The third example is about large language model is document QA. This is it's very interesting story we discussed when we have the chat EDA work. We discussed with some commercial friends, commercial tools companies, and we discussed lots of friends there, and they say, oh, this is very interesting work, but our real requirement is not the flow generation. The actual real requirement is the tool QA, how to handle the customer questions. So we start working on this so-called EDA tool document QA. So this is the flow we construct. We leverage the IAG work. Basically, we have the large language model here. Here we don't fine-tune the model. Instead, we get all the data locally and we construct a vector database. When user asks a question, we will analyze the question, get the embedding of the question, and later we compare the user question embedding with all the embedding inside our vector database to find the most relevant questions, the document. And after re-ranking model, we send relay document into large language model as additional information, and then large language model will output answer. This is very classical, basically very classical work usage of the large language model. But by the way, you can think about when we have the new data, whether this data will be injected into a large language model using fine-tuning, or the data could be stored in vector database. This will be a very interesting question. And here I show you the motivation why we need to have a customized IRG flow, or why we need to have a customized the vector database. So when user asks the question, what is the role of primary input in logic synthesis? When we look at the local document, there are two segments. The segment one said primary inputs are external inputs to the circuit. And segment two said this section explains the role of primary output in logic synthesis. When we're trying to compare the similarity between all these two segments with the input question, when we're trying to compare only based on the word or semantic similarity, we will see document 2 has more words appears in the question. Maybe the similarity could be better, but if you have domain knowledge about EDA, you will know that the question is about primary input. So document 1 or segment 1 is the right section you should pick up, fitting into the large language model. Inspired by this example, we have very strong motivation to find a good link between the user question and document to highlight the keywords in the EDA domain. But it's really hard to list all the keywords in the EDA domain. What we should do, we were trying the automatic synthesible flow to generate, given the question, which we generate the positive sample, and then we do some annotation to generate the hard negative sample. By this way, we provide guideline to the IAG flow, say what could be the better answer to the question. And beside the rack flow fine-tune, the re-ranking thing, we also do the fine-tuning to the large language model. We don't fine-tune using the local data, but we fine-tune using two textbooks of the EDA to make sure our language model nowadays has enough basic knowledge about EDA. We also feed the high quality EDA tool or QA document into the fine-tuning as well. So here is the performance after our large language model fine-tuning and also the RAG flow. We get much better performance compared to all the vanilla RAG flow. And even we don't do fine-tuning, we get also good enough results. And also, this is not the end of the story. Very recently, we also received some requests from the customers, and they argue that the QA flow should handle the user question with image, because some user probably may just take a picture, say, this is output, please answer the question. So we also fit the user image and along with the text description into the model. So if you are familiar with the learning model, you will realize that this is a multimodality thing. We should align the image along with the text into the vector database to do the RAG. And this related work was published in ICK this year. And also we compare with the other vanilla RAG flow and other STOTA using multimodality, we can get a better thing. So now let me summarize a little bit about the future. What will be the new direction? Before that, let me recap how machine can understand pictures. So this is a very, very famous example about RCN. This is a region-based CN to do object detection. Also, object detection is a very concrete, discrete problem. We're trying to identify discrete object from the image, but let's look at the pipeline. First, it will generate a bunch of the ROI, so-called region of interest, from the proposed method. Usually we will generate about 2,000 the ROI regions. And later we do the scaling to scale or warp all the region into the same size of image. The main reason is that the backend, the classification model can only fit the unified input image, input dimension. And later the classification model will generate the class for each ROI region. Besides that, it will also the real location, real size, and real shift. If you are familiar with the classification model, you will realize that before the softmax classification model also do all the regression thing. Basically, we will regress the score for each category. Okay, the softmax only pick up the. So in summary, although object detection is a very discrete task, in the pipeline, we are doing a bunch of the small regression tasks. And in general, machine learning leverages a overall regression task to understand the picture. When we look at the how machine learning can understand the text, this is also a bunch of regression thing. Given the input text, we will predict the next token. And then the predict token will fit into the input. Using the new input, we will predict the next token, and then next token, and next token. So we try also a pipeline of regression model to understand the text. But it will cause a huge challenge into the AI using regression only. For example, there are many in the EDA. We have many combinatorial problems using the left example. So this is graph. When we're trying to find a legal graph coloring problem, say these two nodes should be assigned to different colors, and this is a legal three coloring problem. And if you think about how learning can help for graph coloring, at first glance, the idea will be super easy. We get a bunch of data, and we can leverage graph neural network to do graph coloring and do node classification and to guess the color for each node. But in the combinatorial problems, we have the rotation stable things, which means when we change the red color to blue, blue color to green, and green to red, we will see this node has legal color as blue. We can also change the rotation, do the color rotation using it via another direction. So when red to green, green to blue, blue to red, we will see for this node, green color will be also legal one. So when we summarize all the data, we will see green, blue, green all happen in the label data, which means it provides no useful information at all. Okay, so regression thing cannot be directly applied to solve the graph coloring problem, or it could not be directly applied to solve the design rule checking problem. And how large language model to resolve this? I show you one example. About 2 years ago, when GPT-4 was first released, I asked the GPT the question. I said, I have the tensor A, like this dimension. I have the another tensor B in this direction. That in this dimension, please calculate the matrix multiplication. And this was the answer provided in 2 years ago. The GPT-4 said the matrix A is a dimension with 4 by 5, and matrix B is a dimension with 5 by 2. So the dimension align with each other, we can calculate the matrix multiplication like this way. And it provides answer at the time. At first glance, this is a very perfect answer because it provides correctly. But I manually calculate the answer. The answer is on the right side. When we compare my answer with GPT-4 answer, we realize they are very different, super different, right? Even the positive and negative are not aligned with each other. I was very happy that I thought I figured out a bug from GPT-4. So that happened about 2 years ago. Still 2 years ago, basically 2 weeks later, when a friend visited me, I tried to explain my observation to him. I said, hey, you know what? I realized a bug in GPT-4. So I showed that same answer again. And I realized only after 2 weeks, this is a new answer from GPT-4. It said, okay, based on the information A and match B multiplication using this way. And it called the torch library to do the match multiplication. And I didn't show the answer, but it got the correct answer now. So it really teach me one thing. Large language model is more like a human being. We can call tool to do matrix multiplication. Probably we are not very strong to do the logical calculation directly. Going back to the EDA domain, and after several decades of development, we have developed lots of the very strong tools to solve each small problems, like mathematical formulation, approximate algorithm, dissect, SMT, dynamic programming, linear programming, integer linear programming, flow-based methods, search-based methods, and so on and so forth. And we think about which learning model could be replacing any of model here. Probably the answer is no. No one could be totally replaced by a learning model, but some of them could be enhanced by learning model. Moreover, learning model could be useful to solve the region in the middle. Okay, and from personally, I believe there could be one of the future direction of the large language model. Think about how to link or mix all the tools together to make our overall EDA flow better. And so nowadays we have seen some application about the RTL generation, tool script generation, and flow debugging. But there are also many applications like tool parameter optimization, layout level optimization, more importantly, we have the education purpose or education application toward not just about the university, but also toward the customers. And there are of course, many challenges in large language model. For example, security, how we make sure the language model could answer correct information, not leading to some hallucinate. And another thing is about the privacy, how we make sure the model answer were not leaked IP. So there are lots of things to discuss. I guess that's all for my today's question, the talk. Thank you very much.
Okay, thanks, Professor Yu. Okay, so now we can take questions from the audience. If you have any questions, please type your questions in the Q&A box. Okay, you can see it in the bottom of the room. Okay, so I think I already see 2 questions and 2 feasible questions. And yeah, before that, I actually have one more question. I have one question first. Okay, so I think you talked about yeah, I think for today's talk, you are not just talk about LLM for EDA. You also talk about before that we have a ML for EDA. Okay, so and then you talk about applications, not just your work on the RTL gen. Okay, script generation, and also the documentation QA. Okay, and then you talk about your recent work published in ICK 2025. Okay, and you also mentioned that the multimodality, right? So I think recently there are many people are very interested about agentic AI. Okay, so could you please comment for some like direction of this or research apply for agentic AI for EDA? Yeah.
You mean genetic AI? So I mean,
Yeah.
apply large language model to do
A-
generation.
agent, no, agentic AI. You use the agent. Okay, use a multi agent to conduct different tasks. Like you mentioned, you have a multimodality. You have one agent to handle the image comprehension, another one doing the output generation. Yeah, something like that.
That could be a very natural extension to leverage the knowledge about the large language model. One way is that we provide several model lead by a general agent, and different agent could do different tasks. Or on the other hand, we can look at the agent stuff and think about one particular application. We can construct a kind of graph to understand the task in the graph. We have a bunch of the nodes, and different node we can call different function or tools to solve this problem. And large language model can lead us to jump within between the nodes in the graph. There could be a emerging the topic and direction in large language model, because there will be less and less company capable doing the pre-trained model, and more emerging company will do the agent things in different domain. I'm sure EDA could be a very suitable domain to develop its own agent handling of digital design or analog design. That could be one very important thing. And I'm sure there will be lots of the discussion and interesting things to explore about the boundary. So when we have the agent, some tasks could be handled by the large language model. For example, we can directly apply large language model to generate the test bench, to generate the RTL, but we still have some tools. We should think about one task should be handled by language model directly, or it should be handled by some classical or traditional tools. By this way, language model can mix tools together to provide a very diverse and powerful capability to run the flow. So there will be the huge space to explore, much larger space than we have done before.
Mm-hmm. Yeah, sounds very good. I think it's a very fascinating area, very exciting area. A lot of work can do for. I think we can graduate many PhD students working on this direction. Okay, thank you. And so Bei, could you look at the 3 questions in the Q&A boxes, okay, and try
Let me
to
see.
answer. Yeah, please.
Okay, the first question from TB asking, he said, I guess there may be opportunities for creating more complex gates that algorithm can work with, but engineers may have trouble using them by hand. Is there any work in doing so? For creating more complicated gates that algorithm can work with. I guess it's talking about in the scenario of the gate generation. There are some recent work leveraging or combining the logic sensor and gate generation together, but there was no work really leveraging large language model for gate generation. But when we think about the gate generation, one possible related work is about the operator generation. So when we run inference in the CNN or large language model, we should think about very efficient implementation of the operator. And there are several companies trying to leverage the large language model to think about their assembly language level code for the inference. That could be one thing, but I don't see any work talking about the gate generation, because the complete gate should be applied or should be understood by logic synthesis tools. So this is my quick answer to the first question. For the second question, large language models are particularly efficient in generating tasks. Should we focus on constructing task-specific template to better guide the large language model? Or should we embed the large language model with traditional analytical framework, enabling them to align with the existing conventional method? So I guess the question is about, we have one large language model. We have the classical flow. Which flow should be dominating? Should large language model call traditional flow, or traditional flow call large language model? I saw 2 styles before. Personally, I believe if large language model could, yeah, it's hard to say. I believe some EDA companies, they try large language model as a chatbot inside the flow. So traditional the tool can dominate the large language model in the tool. But there are some new agent companies where large language model will dominate the traditional tool. So there's no concrete or clear answer to the question. The third question would be, why do we need large language model for Verilog generation? We have high-level synthesis or EDA tool for that. This is a very big question. So I only can provide my personal answer. For high-level synthesis tools, we given the C code, we generate Verilog. And of course, we can synthesize given the C, but the PPA or performance using high-level synthesis has a limitation. Their area or power has some problem, and also the generated the Verilog code is not easy to understand using high-level synthesis. So this is one side. So we still have very strong motivation when we try to explore the boundary, performance boundary of the Verilog. we should generate the Verilog code directly. So there is a still huge, very strong motivation generating Verilog directly. So this is my quick answer to your question. Oh, I saw two other questions. Are there any large language model applications in analog mixed signal, such as topology generation, sizing, placement, routing, simulation, and heuristic extraction? Which one do you think is more promising in exploring and what's investing time in? So there are already several work applying the large language model into analog domain in the topology generation and also in sizing. I didn't see much thing about the placement and routing, but here I can provide a quick comparison between the digital world and analog. In digital, we have RTL. So basically, we can apply large language model as a compiler to generate RTL directly. Then we have a very concrete flow to transfer the RTL into the netlist and then layout. But in analog domain, we have to generate topologic or schematic view directly. We don't have the RTL thing. For sure, you will mention about Verilog A thing, but Verilog A, it will be more like the verification purpose. This is not, it can not be integrated into the analog design flow. So in analog domain, we should start from very low level. So yeah, for sure, there are some BH work or TED work and other work. They're using Python level thing to generate the netlist or topologic in analog. But let's see whether it could be successful. But I should say this is much more complicated than digital, because in digital we have a high level RTL. In analog, we should start from netlist. So this is my short answer to the question. Okay, I guess that's all for the question.
Yes, okay, thank you, Bei. Yeah, I think people are very interested in your talk because this is a very fascinating area. I think many people are working on that. Okay, so if there's no further questions, I would like to thank Professor Yu, of course, and also everyone to join the talk today. And note that we actually record the talk, and this recorded talk will be uploaded at the CEDA presentation library soon. Okay, and I would like to mention that we will have another CEDA virtual DLO talk in September by Professor Alberto Boscio. Okay, he will talk about the trustworthy AI in EDA. Okay, so please stay tuned and see the update from the CEDA website. Okay, so thank you. Okay, thank you all
Thank you for your
today.
time.
Bye bye.
Thank you, Zhongyi. Bye bye.